Hello everyone. In this video, we'll cover the module Estimation and Inference for CFA Level 1 2025. If you are new to the channel, please subscribe and share this video so that other candidates can also benefit from it. You will find the link to download the presentation in the description box. Let's move ahead. There are three learning outcome statements in this module. We'll cover them one by one. Compare and contrast simple random, stratified random, cluster, convenience and judgmental sampling and their implications for sampling error in an investment problem. So we'll study different sampling techniques in this video. Let's first talk about why do we need samples? Because it is not possible to examine every member of the population and it is not economically efficient to examine every member of the population. So we need to take out some samples from the population and run our analytical methods on these samples to estimate the properties of the actual population. Sampling saves us time and money. There are two types of sampling methods. First are the probability sampling. Probability sampling gives every member of the population an equal chance of being selected. It can yield more accuracy and reliability compared to non-probability sampling. So there is no bias involved in probability sampling because each and every member of the population has equal chance of being selected. Then we have non-probability sampling. It depends on factors other than probability considerations such as sampler's judgment and the convenience to access data. It might generate a non-representative sample because the process is biased based on sampler's judgment and also the convenience to access data. So it will generate a non-representative sample. Let's first focus on probability sampling. So there are different types of sampling methodologies that are covered in probability sampling. We'll cover them one by one. First of all, let's talk about simple random sampling. A simple random sample is a subset of larger population created in such a way that each element of the population has an equal probability of being selected to the subset. The procedure of drawing a sample to satisfy the definition of simple random sample is called simple random sampling. The procedure is called simple random sampling. It is useful when the data in the population is homogeneous. That is, the characteristics of the data or observations are similar. If this condition is not satisfied, then we'll consider other types of sampling methods. Sampling error. Let's see what is a sampling error. It is the difference between the observed value of a statistic and the quantity it is intended to estimate as a result of using subsets of the population. Since we are not calculating the number based on all the data from the population, we have taken out a sample from the population and then we are calculating the number based on that sample. So the difference between the true value of the quantity and the estimated value of the quantity, that will be your sampling error. A random sample reflects the properties of the population in an unbiased way. So a random sampling is an unbiased procedure. And the sample statistics are valid estimates of the underlying population parameters. Sampling distribution of a statistic is the distribution of all distinct possible values that the statistic can assume when computed from samples of the same size randomly drawn from the same population. So that is your sampling distribution of a statistic. Now let's talk about stratified random sampling. In stratified random sampling, the population is divided into subpopulations called strata based on one or more classification criteria. So we decide a classification criteria and then we divide the whole population into different subpopulations. Now random samples are drawn from each stratum in size is proportional to the relative size of each stratum in the population. So the stratum which has a higher percentage of the population will get a higher number of sample drawn. The samples are then pooled to form a stratified random sample. The advantage is that estimates of the parameters produced from stratified sampling have greater precision, that is, smaller variance or dispersion than the estimates obtained from simple random sampling. Bond indexing is one area in which stratified sampling is frequently applied. In this approach, we divide the population of index bonds into groups of similar duration, cash flow distribution, and different types of properties we can use in this case. We refer to each group as a stratum. Then we choose a sample from each stratum proportional to the relative market weighting of the stratum in the index to be replicated. Then comes the systematic sampling. In systematic sampling, you devise a rule to draw sample from the population. For example, that every kth member will be selected until we have a sample of the desired size. The sample that results from this procedure should be approximately random. Then comes the cluster sampling. It also requires the division of classification of the population into subpopulation groups called clusters. In this method, the population is divided into clusters, each of which is essentially a mini representation of the entire population. So what is the difference between stratified sampling and cluster sampling? The difference is, in stratified sampling, we group the data based on a particular characteristic. For example, if the data is of students, we can group the students based on their age. That means we can create groups of different aged students. For example, 15 to 20 in one group, 21 to 25 in second group, and then 26 to 13 third group. So the samples in a particular stratum have similar characteristics which are different from the other stratum. So that is your stratified sampling. But in cluster sampling, you divide the populations in such a way that each cluster represents the population. That means each cluster has the data that is pretty much similar to all the population. If all the members in each sampled cluster are sampled, this plan is referred to as one-staged cluster sampling. If a subsample is randomly selected from each selected cluster, then the plan is referred to as two-staged cluster sampling. Now let's see, this is your simple random sample. That means you are simply picking up the random data from the population. This is your systematic sample where you are taking out every third member of the population. This is your stratified sampling where you have divided the data based on their characteristics. This is the yellow samples, these are the green samples. Then you take out random data from each of these stratum to create your sample. Now this is a cluster sampling technique. In this case, you create clusters such that these clusters are representative of the whole population. Then you select some of these clusters. Now let's talk about non-probability sampling. These methods do not rely on a fixed selection process. They do not rely on a fixed selection process, but instead they rely on researchers' sample selection capabilities. They are biased based on the researcher. There are two types of non-probability sampling. First is convenience sampling. In this method, the element is selected from the population based on whether or not it is accessible to a researcher or how easy it is for a researcher to access the element. So the convenience of accessing that data is the basis of that data being selected. The advantage of convenience sampling is that data can be collected quickly at a low cost, but the samples are not necessarily representative of the entire population. Second type is judgmental sampling. This sampling process involves selectively hand-picking elements from the population based on a researcher's knowledge and professional judgment. That means the researcher is using his judgment to select the sample. Explain the central limit theorem and its importance for the distribution and standard error of the sample mean. So first of all, let's see what is the central limit theorem. The theorem states, given a population described by any probability distribution having mean mu and finite variance sigma square, the sampling distribution of the sample mean x bar computed from random samples of size n from this population will be approximately normal with mean mu and variance sigma square by n when the sample size n is large. So what does the theorem say? It says, suppose you have a population, you have a data population, your data looks like this. So we can clearly see that this distribution is not normal. Now we take random samples from this population of size n, and when we calculate the sample mean and variance from all of these samples, the theorem says that the distribution of sample mean and variance will be approximately normal. And the mean of this distribution will be mu equal to the mean of this population, and the variance will be sigma square by n. Now the only condition that is required for this condition to hold is that the n should be large. It should be greater than 30. So the sample size must be greater than or equal to 30. What is the standard error of the sample mean? For sample mean x bar calculated from a sample generated by a population with standard deviation sigma, the standard error of the sample mean is given by, if we know the population standard deviation sigma, then we can use this formula to calculate the standard deviation of x bar. If we do not know the population standard deviation, we only know the sample standard deviation, that is S, then we can use this formula to calculate the standard deviation of x bar. Both the formulas are similar, but in this case we are using the population standard deviation. In this case we are using the sample standard deviation. The central limit theorem tells us that when we sample from any distribution, the distribution of the sample mean will have the following properties. The properties of the sample mean as long as our sample size is large. The distribution of the sample mean will be approximately normal. The mean of the distribution of x bar will be equal to the mean of the population from which the samples are drawn. The variance of the distribution of x bar will be equal to the variance of the population divided by the sample size. Describe the use of resampling, bootstrap or jackknife to estimate the sampling distribution of a statistic. Bootstrap, as we discussed in the last video, is one of the most popular resampling methods. It uses computer simulation for statistical inference without using any analytical formula. So this is the formula to calculate the standard deviation of sample mean. Jackknife is another resampling technique for statistical inference of population parameters. Unlike Bootstrap, which repeatedly draws samples with the replacement, jackknife samples are selected by taking the original observed data sample and leaving out one observation at a time from the set. That is, we are not replacing the data in the sample. Jackknife method is most often used to reduce the bias of an estimator. For a sample size of n, Jackknife usually requires n repetitions, whereas with Bootstrap, we are left to determine how many repetitions are appropriate, because we are not replacing the data, we are leaving out one observation every time we take out a sample. So jackknife, for a sample size of n, jackknife will need n repetitions. But with Bootstrap, since we are replacing the data, it's up to us that how many repetitions do we perform. So this is it for this module. I hope you liked the video. Please share this video so that other candidates can also benefit from it, and subscribe the channel to get notified on my future videos. I'll see you in the next video, in which we'll cover hypothesis testing for quantitative methods. Until then, keep studying and share your doubts if you need my help. Thank you very much.